In this video, we are going to prove that 1 minus 2 square plus 3 square minus 4 square plus 5 square and plus all the way to the n term, which is minus 1 raised to the power of n minus 1 n square equals minus 1 raised to the n minus 1 times n plus 1 over 2 for every positive integer n. So we are going to use mathematical induction to prove it. And the first thing I want to do is to let Pn be this statement. Be 1 minus 2 square plus 3 square minus 4 square plus and all the way to plus minus 1. Okay, minus 1 raised to the n minus 1 n square equal minus 1 raised to the n minus 1 n times n plus 1 over 2. Okay. Now once we have this Pn, let's just begin with base step. Okay. So base step. So what is the base step in this case? So try to let n to be 1 first. Okay. When n is 1, what do we have? Okay, I will plug it into here. So when n is 1, we need to have just one term, right? So let's try to plug in n equal 1. So we gotta have minus 1 raised to the 1 minus 1. 1 minus 1 times 1 times 1 plus 1 over 2. So we gotta have minus 1 raised to the 0, 1 times 2 over 2. So we gotta have 1 times 2 over 2. And these 2 will be cancelled, so it turns out to be just 1. Okay, which is 1 square, right? Which is 1 square. Okay, so that means that P of 1 is true. Okay, P of 1 is true. Now, what about when n equal 2? Let's see where it is. When n is 2, try to plug in 2 into this n. So what do we have? We gotta have minus 1 raised to the 2 minus 1, 2 times 2 plus 1 over 2. So we gotta have minus 1 to the 1, 2 times 3 over 2. And it turns out to be minus 3. So what is this minus 3? Minus 3 is 1. Okay, it's 1 minus 1. Minus 4, which is 1 square minus 2 square. That's it. So when n is 2, we're going to have this first 2 terms. So this means that P of 2 is true. Okay, P of 2 is true. So that's what we have. I think P3, P4, P5 will be true. So we already have the base step. So let's go to the inductive step. Okay. So for inductive step, what do we have to assume? So I'm going to assume that P of k is true. Okay, is true for all integer k. Okay, for all integer k, and k must be less than something, less than m. Okay, and m must be greater than or equal to 3. Okay, so I use the strong induction. We already have P1 and P2 being true, and then we are trying to show that P of M equal to 3, P of 4, P of 5 are all true. Okay, by assuming that P of K is true for all integer K, where K is less than M and M is greater than or equal to 3. So we will have the case where P of K is true when K is less than 3, right? Can K less than 4, less than 5, less than 6, and all the way and so on. Okay? Once you can show that P of K is true for all K less than M where M is greater than or equal to 3, you need to show that. What do we have to show? We need to try to show that P of M is true. Okay? Try to show that P of M is true. Got it? So now, what can we do with this? How to show that P of M is true? Okay? So let's take a look at this statement right here. So we will assume this. So since P of K is true, what do we have? Since P of K is true, okay? P of K is true under this condition, okay, for all K where K less than M. So we can say that P of M minus 1 is true, right? Okay, P of M minus 1 is true, and try to show that P of M is true. Okay, so now what happened to P of M? So we gonna have, okay, let me write PM. Just substitute PM minus 1 into here. So we gonna have 1 minus 2 square, actually it's 1 square plus 3 square minus 4 square and plus all the way to minus 1 raised to the M minus 1 minus 1. M minus 1 square equal to minus 1 raised to the M minus 1 minus 1 M minus 1 times M minus 1 plus 1 over 2. Simplify this equation, so we gotta have this equation, okay? So 1 minus 1 becomes, what does it become? We gotta have M to the minus 2, okay? Then, what next? So we gotta have M minus 1, M to the minus 2, okay? And M minus 1 times M, okay, over 2, all right? So this is what we have from this equation, okay? And then try to show that P of M is true. So we need to add one more term. So what do we have next? So we gotta have to start with this term, okay, and add one more term. So I'm going to add this term plus minus 1. So this one is now M, right? M minus 1. Okay? Plus what? Plus M. Okay, what is it actually? This term must be M. M squared. Okay? m squared. And the first m minus 1 term is this one here. So we're gonna have minus 1 raised to the m minus 2 times m minus 1 times m over 2 plus minus 1 raised to the m minus 1 m squared. And then we try to have equal denominator, okay, or just factorize, right? Okay, let's try to have equal denominator. So we're gonna have minus 1 raised to the m minus 2 m minus 1 times what? Times m over 2 plus minus m to the m minus 1 2m squared over 2. And okay, so this is minus 1 raised to the m to the minus 2. This is minus 1 raised to the m minus 1. So we try to factorize this term. Factorize m to the minus 1. So we're gonna have m minus 1 raised to what? M minus 2. Okay, factorize this m. So we're gonna have, okay, give me a second. We're gonna have m minus 1 m over 2 and plus minus 1. Okay, 2 to the m squared over 2, like this. Great. Then what do we have next? So try to simplify this term. So what do we have? We're gonna have, okay, so we're gonna have minus 1 raised to the m minus 2, and we're gonna have, okay, so try to simplify this term. So we're gonna have m squared minus m. Okay, distribute this m into this, and minus 1 times 2m squared will become minus 2m squared over 2. Then what do we have next? We can have minus 1 raised to the m over 2. And we have minus m squared minus m over 2. And we try to have, okay, we remove this minus sign here. So we're going to have minus 1 raised to the m minus 2 times minus 1 and m squared plus m over 2. And factorize m right here. So we're going to have minus 1 raised to the m minus 1. So we're going to have m plus 1 times m over 2. Okay, is this PM? Okay, is this PM? I'm not so sure where it is. Okay, so we're gonna let n, we're gonna let m to be in front of m plus 1. So we're gonna have m times m plus 1. That's it. Okay, that's it. All right, so this is what we have. Okay, so we have shown that P of m is now true. Okay, P of m is now true. Then what next? So we have shown that by strong induction, okay, by strong induction, we have proved that. What did we prove? We proved that this equation is true for all positive integer n. Okay? For all positive integer n. And this is what we have for this problem. Okay, so we have shown that this equation holds for every positive integer n. And that's it for this video.